Hello, we're going to do an example on magnetic flux. So, actually we're going to start with just a little unit blurb on magnetic flux. So this is a blurb, something I forgot in the last video. The units for magnetic flux, which is always phi sub b. They are, well, do you recall the equation? It was magnetic field times an area times some sine of an angle, which is unitless. So of course the magnetic field unit would be the Tesla, and the area unit would be the meter squared. We use this so often we gave it a name. It's called 1 Weber, and it's named after Wilhelm Edward, I guess, I don't know, Weber. He's a German guy. He was around in 1804 to 1891, so he lived a long life. That is the unit for magnetic flux. Another little thing to note is that 1 Tesla, the unit for a B field, has an equivalence to something called a Gauss. 1 Tesla is equal to 10 to the 4 Gauss. That's the different units for magnetic fields. And just to give you an idea of what a Gauss is, Earth's B field, so B for our wonderful Earth, is about 0.5 Gauss. And so that would be approximately 5 times 10 to the negative 5 Tesla. And so that's the end of our blurb on units. And now we'll do a magnetic flux example. So this will be an example on magnetic flux, and the only one we're going to do, because we'll deal with magnetic flux in different examples as part of our solution. So this is an example on magnetic flux. And so in this example, we're going to say, determine the magnetic flux in a 3 centimeter wide aluminum loop if it is dropped through a uniform magnetic field as shown. And so first of all, we'll need a picture because it should have been given. And we might note that the uniform magnetic field should have been given too. So we're going to say B equals 0.381 Tesla. Why not? That's the magnitude. And our picture will give us the direction. So in this picture, we're going to have our B field directed into the page. So B is given with X's, and I'm going to try to draw them uniformly spread. And I'm going to note that we're going to ignore any effects due to induced currents or anything like that in this problem for now. I'm setting us up to have this similar problem in another section. So what's going on is we have our loop, our aluminum loop, like so. It's got some thickness, and that aluminum loop is being dropped through this magnetic field. And so what I'm interested in is as this falls, if you can imagine this falls it will enter the B field, it will fall through the B field, and then it will leave the B field. And I'm interested in the magnetic flux when it's maximum, or as it's right here inside the B field. So there's our loop still falling, but this is when it has the most, or the entire area of the loop inside the B field. So this has some radius r. And you could imagine, like, when it's here, it's partially inside the field, but mostly outside the field. So we would have a maximum flux and maybe some sort of minimum flux. And then if it gets down to here, we would have no magnetic flux because the B field is not inside the area any longer. So this seems a little bit excessive, but we'll use it again and think through it again later. The point is, we could figure out the magnetic flux through this area at this point. And so that's what we're going to do. Recall the magnetic flux. Pen died. The magnetic flux is equal to, and it's the sum of all the B field lines dotted with any little piece of area that they're traveling through. But like we noted before, and just like we did with electric flux, this will simplify to BA cosine phi. And so what is the angle between the normal to this area and the B field line? Well, the normal we could represent as an x. That would be perpendicular to the surface. And so we could say that phi is equal to 0 degrees. So phi b is equal to BA cosine of 0 degrees, but cosine of 0 degrees is 1. So we get phi b equals BA. And so we could solve. Phi b is equal to, B was 0.381 Tesla, and A would be pi r squared. Well, r would be half of the diameter, wouldn't it? So we could solve by substituting in for r. And r would be 0.015, 1.5 centimeters, or 0.015 meters squared. So that's 0.000225, I think, and we'll multiply by this, and then we can multiply by pi and get our solution. So phi b is equal to, and we have to calculate this. I normally won't do this, but I came unprepared, so we'll have 0.381 times pi. Never round pi. You should always use the symbol for pi. Looks like you can't see the screen there. Always use the symbol for pi, then multiply by 0.015 squared, and we get our solution to be 2.693. And my dogs say it's time to stop. So great example.